delay, folks. Can I have your attention, please? Thank you. This is the second to last week of classes, and the last full week of classes.
All right.
So I'm pretty sure we've got 2 classes next week because class ends on the Thursday, I think. Anybody who has better information than that, feel free to contact me. Yes, sir.
Will we be having you next semester?
Not likely. Not likely going to be having me next semester. I am currently contracted to teach 1XC3, and if things work out with certain applications that I've made, I'll be teaching in the first year engineering program, teaching them programming. Heaven preserve me.
Sorry,
and you know, after if that doesn't work out, I'll probably pick up some courses at Mohawk College.
Oh.
Yes.
Is directed graphs at last?
No, we can cover more. I hope to be able to get it to topic 4. Do shortest path algorithms. It's of course it's 63 slides, so God knows we won't get through it. But no, we still have you know, a good 5 lectures left. So directed graphs, we are going to definitely finish this today, and then be on to the next one the same day. So, any other questions? TAs haven't come back yet, have they? Well, so it goes.
Are you full-time now? Are you like full-time contracted to McMaster or no? Because like there was an email sent out to all the students saying that you were like.
Oh no, I was interviewing for a full-time position.
Oh, okay.
It's a contractually limited appointment, which means basically they bring you in at the rank of associate professor or assistant professor, whichever of the 2 of those is lower. And but it's only an 8-month contract, and like frankly, there should be fewer interviews than months in the contract, in my opinion. But you know, so it goes.
Did you get your results back? Or?
No, I haven't heard back about it yet. Enough of this impromptu chit chat. We should learn some things. So we've been talking about directed graphs, directed graph algorithms. We were just about to do an example of the Kosaraju-Sharir algorithm, which gives us the strongly connected components inside of a directed graph. If we recall, a strongly connected component is a component wherein each of the nodes are accessible inside of a cycle or multiple cycles. The connected component itself, or the strongly connected component, is the maximal cycle inside of the group of cycles represented by this portion of the graph, right? So what that means, you'll notice that 3, 5, and 4 form a cycle within this larger cycle, right? The strongly connected component itself is the largest of all of these ones that includes all of the cycles in there. Make sense? So far, so good? So, so our algorithm here is reasonably simple to understand. Like it's simple to remember, but not as simple to understand why it works. So the first thing that we need to do in order to run this algorithm, to find strongly connected components, we need to calculate the reverse of the graph. The reverse of a graph, of course, perhaps intuitively, is simply the same graph with all of the edges flipped, right? So let's go. By the way, you know that chalk I was complaining about last time? I'm pretty sure it's like less erasable than regular chalk as well. So it's just because like you see this? I'm pretty sure that's that stupid chalk that they were using. So, let's do a small, simple example. I'd like to get through this material and on to the next. So, let's imagine we have a relatively simple graph consisting of 4 nodes, bidirectional edges on 1, 2, 3, and 4, and we have some edge between. Now, it should be reasonably intuitive to everyone in the room that in terms of our strongly connected components, we have 2. There we go. You can tell how long someone has been a prof by how well they do dotted lines on the chalkboard. So, that being a particularly bad example. So, the first thing we have to do is to compute the reverse of the graph. So if this is G, the reverse of G would look reasonably similar I'm kind of like, I have down on the left here and right up, and here I have up on the right and down on the left. That's just to show that like I'm taking this one, reverse it, taking that one, reversing it. There's no, like, graphs don't care at all about like what side of a bidirectional relationship they're on. I could just as easily have drawn them like this. In fact, you'll see that often. So don't let it fool you. I'm not introducing more complexity. And of course, this edge gets reversed this way. So there we go. So we are going to run depth first search on the reverse graph and compute the reverse post order, which should be relatively quick. Let's first set up our adjacency array. So 1 connects to 2, 2 connects to 1, 3 connects to 4 and 2, and 4 connects to 3. There we go. Marked, and our reverse post order will keep it bottom. So, starting with 1, because it's a reasonable place to start. So, we call depth first search on. That is very annoying. Bloody Windows. Like, why is it logged out? Hate it so much. Anyway, so we check that off. We find 2, open up a depth first search on 2. 2 is visited. 2 has nowhere to go, so we close it, add 2 to the reverse post order. Then we close off 1, as it has nowhere to go, add that to the reverse post order. There we go. Now we check for 3. Depth first search on 3, of course, finds both 2 and 4. 2 has already been checked off. So depth first search on 4, close that off, 4, close that off, 3, there's our reverse post order. Cool. So, next, we run depth first search on G, not G reversed, considering the vertices in reverse post order. So, let's just see how we're going here. So, in this example, this larger example, the reverse post order procedure generates the following order with 1, 0, 2, 4, 5, etc. During phase 2, we run depth first search on the graph, not the reverse of the graph, considering vertices in the order given by the first depth first search. So, we check these in the order given by the first depth first search. So, where's my chalk? Where's my good chalk? Ah, this. So, as we're checking these, right, you'll notice that if we keep these lists of, if we keep an ordering, doesn't necessarily have to be a reverse post ordering here. If the vertices visited during the search, starting with each of these numbers in the reverse post order, that will give you your clusters, right? So, yes. So let's just see how that works quickly. Remember, we're considering G now. So, if we were to do out our adjacency array, one is, of course, pointing to 2. 2 is pointing to 1 and 3. 3 is pointing to 4, and 4 is pointing to 3. So we are considering things in reverse post order. So the first one we compute, just set up our, let's just say, let's call this ID. So I'm changing things slightly. Rather than keeping an array of marked vertexes, I'm now going to be swapping booleans for integers. Each time we have computed a reverse post order based on, or each time we compute a depth first search based on one of these, I'm going to increment the number I'm recording and in that array, and that should give us unique identifiers for each of the strongly connected clusters. Make sense? Sort of? Have I lost everybody at this point? Anybody still following? Okay, a couple of people at least. So, considering first depth first search on 3. So, we'll call that 0. 3 finds 4. 4 finds 3, but that's fine. Mark it 0. Close that out. Close that out. There we go. Then, considering 1, depth first search on 1. 1 finds 2. 2 finds 1 and 3. 3 has already been allocated, so we don't do that one. Call this 1, call that 1, close that off, close that off, and there we go. You'll notice 1 and 2 end up in one cluster, 3 and 4 end up in the other. This example is too small to hit all possible edge cases for this algorithm. However, hopefully this gives a sort of a general overview of how the algorithm operates. Question?
Yeah, why do you start with 3?
I started with 3 because the whole, it's very, very important in this algorithm. The first depth first search on the reverse of the graph, the whole point of that is to extract the reverse post order, because the reverse post order is the order in which you need to consider the vertices in the second half of the algorithm. Otherwise, it doesn't work. Yes?
Why don't we first start at the graph and then start with the reverse graph? In this way, we don't need to compute the reverse graph.
Sorry?
Why don't we first run DFS on the graph and then run it on the reverse graph?
No, we run it on the reverse graph first and then the regular graph.
Yeah. Why we don't first run it on the graph? So we don't need to compute the reverse graph. In order to run DFS on a reverse graph, we need to first get the reverse graph.
Yes. Yeah. So,
But why don't we just run the DFS on the graph? Then we can get the reverse graph.
the depth first search does not compute the reverse graph.
Let's use the reverse post order array.
No, that's not what that does. A reverse graph is simply a graph with all of the edges reversed, right? The reverse post order is like it's not a way it bears no relation to the reverse graph. They're different things you're computing. So remembering from our previously covered material, the reverse post order is one possible topological sort of the graph, right? So it's not like, it's some way that you can arrange the nodes linearly so that all of the arrows are flowing down, right? But the reverse of a graph is literally, I take this edge, I flip it, I take this edge, I flip it, I take this edge, I flip it. Like, it's still a graph. This is not a graph. This is an ordering of nodes. Does that make sense? Okay. Question?
So if it was A sufficient, then each number would have a unique ID?
Yes. Yeah, exactly. So because a strongly connected component requires a cycle, if the graph was acyclic, every node in the graph would be a cluster of one, right? Because that's how we've defined these components. Any component containing one, like any one item is still a component. Make sense? Cool. Any other questions? Yes.
So when you're doing the second part, with the DFS on the graph, are you also just following the order exactly, or are you starting at 3 and then looking at the adjacency matrix?
That's a good question. I'm starting at 3, and I'm looking at the adjacency matrix, right? And you'll notice that the order here is 3, 4, 1, 2, right? Because 4 had been marked during my search of 3, I skipped it in the reverse post order. Like when I was considering my starting points for DFS, I did that one checked off this one and this one, so I skipped this one. Then I went to the next unchecked vertex, and that checked off the rest of them, so I was finished. Cool. Any other questions? Okay. Good. So, if you'd like to see what the Java code looks like, I recommend taking a look at that on your own time as self-studying. So, talking about our runtime now. Runtime is proportional to the magnitude of the set of vertexes plus the cardinality of the set of vertexes plus the cardinality of the set of edges. This should be, at this point, you should be like well trained in algorithms enough to not need a proof of this. What is the algorithm that is used in both subsets or both substeps? It's depth first search. What is the complexity of depth first search? It's this. Yeah. It's V plus E. If you run an algorithm twice, does that increase the complexity? No. It might increase the size of the constant, but it does not increase the proportionality. Therefore, since all we're doing is 2 applications of the depth first search, this is as much as, like, our runtime has not substantively changed, at least in its proportionality. Obviously, running something twice takes longer than running it once. But again, we're concerned about proportionality to the input. Make sense? Any questions about directed graphs before we move on to edge-weighted graphs? Yes?
So you know how to run an average, but why it works?
So why does it work? So the one thing that you have to be concerned with, say you wanted to compute the connected clusters and you were just using the marked vertexes from a depth first search to compute that, right? If you start here, well, no, actually, let's do the regular graph. If you start at 4, right, you find 3 and 4. That is a connected cluster. Like, you're guaranteed to find all of the vertexes inside of the connected cluster, right? However, if you start searching at 2, for instance, you'll find all 4 nodes in this graph. So it's a property of the depth first search that it finds, at minimum, all of the nodes in the connected cluster that you start from, right? But it might find more than that, right? So, and I don't have slides for this, so I can't give you a proof. But so, what the purpose of doing the reverse post order is, I think it's easier if I do the topological sort. So, if we sort of lay these guys out, well, actually, you can't do a topological sort because they're, well, I mean, you can, but it'll have back edges. But, so, it's kind of like you only have, like, the arrow that's connecting things here has only one of 2 states. It's either flowing forwards or it's flowing back, right? If you consider starting at the same node, right, depending on the orientation of this arrow, you're either going to get the minimal, you'll either get just the connected cluster, or you'll get more than you want, right? So, I think it might be easier if we consider both cases, right? So in this case, 4 will find all of them. In this case, 4 only finds 4 and 3, right? So
So is that now revised graph, that's the same thing. We go from 2, we can find it's like very equivalent from my perspective. For that revised arrow in below, very equivalent because just the different elements, different nodes can go through the same thing. So
yeah. Also, if you're so, what are we guaranteed by having the reverse post order, right? We're guaranteed that nodes on the end will be downstream of nodes further up in the list, right? According to the reverse post order. So basically, the reverse post order is saying these guys are downstream of these guys, right? So if you reverse these connections that connect to these clusters, right, then what you've done is you've guaranteed you're in the situation where the upstream components must be downstream. And then if you check them off in order of them being downstream, right, then, like, we check them off in order of being downstream. This prevents things that are flowing into them from also including them, right? And so it's kind of like if you build it up from the bottom in that manner, then you are guaranteed to only keep to the minimum depth first search finding. Make sense? Excellent. Excellent question. Excellent question. Any other questions? Yes?
Will the reverse post order of the reverse class be the reverse of if you did the reverse post order for the same graph starting from the same initial node?
I don't know. I'm not going to make any claims about that. Any other questions? Okay. Well, so much for directed graphs. This is shortest path algorithms. So, question? Oh, yes. Yeah. Very poor Wi-Fi. Also, my computer is locked up. Okay, I'm just going to talk about it. Oh, there we go. While my computer figures its brain out. You should be able to see it now. So, we are going to talk now about minimum spanning trees. Now, a spanning tree is something we already know how to compute, right? Which of the two algorithms computes it? Depth first search or breadth first search? Trick question, they both do. Ha! You gotta be sharper than that this morning. Ha! So, anyway. As indicated from the midterm, I like to put trick questions like that on tests. So, just be aware of that, okay? So, I never give them many points, though. I'm not going to make you, pass or fail the course based on a trick question. That would just be cruel. It is a nice way to see who's paying attention, though. So, so we have now, we're going to talk about yet another variant on graphs. So far, we have not been concerned about characterizing the edges between vertices much, save designating endpoints and perhaps direction. Now, we are concerned about these graphs having edge weights. This instantly makes this a much better model of physical reality. You might imagine that an edge-weighted graph might represent a series of cities and a distance between them in kilometers, or perhaps more accurately, the distance of a trade route between the two cities, because that's the more pertinent metric. At least it was before the age of air travel. So, edge-weighted graph. All of our, so we're shuffling backwards a little bit now, back into undirected graph territory, right? We're going to not worry too much about directions on these for the time being. Instead, we're going to explore what implications placing numbers on these edges might have. So, this is the problem to which the traveling salesman problem applies, right? So, I don't think we're going to talk about the traveling salesman problem, but it's a very, very famous problem in algorithms, which notoriously has a very bad solution. So, the traveling salesman problem is pick one path through this network of nodes such that you are visiting every node and yet minimizing the distance, minimizing the weight of all the edges you pass through, right? The brute force solution, and we're going to find that brute force solutions are very quickly becoming out of style. The brute force solution is to try every single possible path, right? Now that's going to be a lot. It's n factorial, in fact. The particular problem that we're currently addressing, though, a related problem, but not quite the same problem. We are talking about computing the minimum spanning tree. It's kind of like a more general version, or a less general version of the traveling salesman problem, in that we are not interested in computing a single path between every node in the graph. We are interested in computing a tree which spans every node in the graph, which also has the minimum edge weights, minimum total edge weight of any possible tree that spans the graph, right? So this is still, brute force solutions are now completely beyond, you cannot write a brute force solution to this problem and expect to get a result in your lifetime, even for reasonably small graphs, right? As soon as you, have more than 30 or 40 nodes, you're starting to talk about uncomputable quantities in terms of brute force solutions. So, so this is fine. Any questions so far? In concept, adding numbers to these edges shouldn't be too much of a conceptual leap, hopefully. So, just reminding ourselves the definition of a spanning tree. A spanning tree must be connected. A spanning tree must be acyclic. And a spanning tree must include all vertices. Good. A minimum spanning tree of an edge-weighted undirected graph is a spanning tree whose weight, that is, the sum of the weights at its edges, is no larger than the weight of any other spanning tree. So, that is to say, it may not be uniquely defined, but the solution must be, you know, if you have multiple spanning trees that are tied for first place, shall we say, your solution can be either of them. So, a brute force solution, trying all spanning trees, is ridiculous, and nobody should attempt it. If you find yourself beginning to write a brute force algorithm for this algorithm, you need to take a rolled up newspaper and whack yourself on the back of the head with it and say, no, I took 2CO3. I know better than that. So, our solution is to use a greedy approach, and we're going to make a simplifying assumption that all edge weights are distinct. This helps mitigate the multiple trees tied for the same value problem. So, before we get into that, we should talk a little bit about how we are setting up our data structure. So, in Java, we are setting up a new class, or modifying an existing one. Actually, I'm not sure we had a class for edges before. Edges are very simple. All they're doing is taking the integer ID numbers of two vertices in the graph and adding to that a weight, which we're storing as a double for some reason. Not quite sure why, considering these are all integers, but you know, so it goes, right? So, very easy. You know, we have a constructor. We return either endpoint. We have a method for that. Either and other are different methods here. And compare to edge compares edge by weight, so that we know if one edge is greater than another. You know, this is sort of the standard thing that the textbook does. Abstract out a comparison method, so that, you know, if you had something fancier than this, some fancier means of comparison, then that would be, you would be able to do that. So, so it goes. Any questions about that? Should be relatively straightforward. All we're doing is taking two vertexes and adding a weight and calling that a class. Good. Scratching your head, not a question? Okay, cool. So, it says that these are bag objects, but honestly, I'm not sure why we wouldn't just use lists like everything else, but you know, so it goes. So our adjacency graph, or our adjacency matrix is now slightly more convoluted. It has not fundamentally changed in character, however. We have one entry in the adjacency matrix for each vertex in the graph. Note we have 7 vertex, 0 to 7 here and 0 to 7 there. Note also, each one of these points to a series of edges, which are specified vertex 1, vertex 2, and weight. Note that each entry in the adjacency matrix leads to a bag of edges, all containing the number which is being, originates in the adjacency matrix. In theory, that makes the second number redundant, but since we're collecting everything up into, into classes now, we'll just leave it. One important thing to note, if you examine 0, the number that we're looking up in the adjacency matrix might be the first or the second of the two vertices specified. So, you know, it might be one or the other, but it's certainly one of the two. Make sense? So fundamentally, the purpose of the adjacency matrix is to be able to look up the adjacent nodes via their edges, or to look up the adjacent edges. Yeah, actually, pardon me. Let me rephrase that. Prior to this formulation, the purpose of the adjacency matrix was simply to direct us to the adjacent vertexes, right? We specified the adjacent vertexes by their integer ID numbers. In this case, we are specifying the adjacent edges. Edges are now first-class members of this data structure. Edges are not sort of these incorporeal results of data structures which connect vertices together. They now are first-class members. They have data that's contained in them, so they have to be represented physically. Make sense? Question?
Can you repeat why you said the second value is redundant?
Oh, well, if you have a data structure that points, like, if you have adjacency 7 and 7 is like, each one contains a 7, then that's redundant. You could replace these with a data structure missing the second vertex and just use the one that's not the number being pointed to in the adjacency matrix, and that would, like, you wouldn't lose any information. So it's kind of like a side point, you know. Any other questions? Generally, we don't really care about keeping a couple of extra variables. Yes?
The matrix is, sorry, that age, some of the age are not marked right, I think. For example, the first one, we see 0, 0, 6, 0, 0.58, that wrong, right?
0.6.58.
Because the second one is 0, 2, 0, 4, 0, 7, but the first one is 6, 0. Is that?
Oh, no, it's, the ordering between the first two elements doesn't matter.
Oh, okay.
Yeah. It'll be one way or the other. You'll notice that if we look up 6, it's got 6, 0. It's got the same representation here.
Oh,
So
if that's a direct without matters.
yeah, so yeah, because we're undirected, it doesn't matter. If it was directed, it certainly would matter. I would just point out that probably what's happening in the back end behind all of this is that there would be like one edge object declared for each edge specified in this initialization list. The adjacency matrix would simply contain reference to those edges. So this point here, 60.58 and 60.58 here would both be pointers to the same object. That would make sense to me. Yeah. You'd save a little bit of data. Not much, but you'd save data proportional to how much data you're cramming into that class, right? Cool. So, let's discuss what a cut is. Lord knows I don't get my cut. You guys aren't getting your cut either. Everybody wants a cut. So, a cut in a graph is a partition of its vertices into two non-empty disjoint sets. So, in other words, you take all of the vertices in the graph and you throw them in either one pile or the other pile, right? Another way of thinking about this is you draw a line through the graph separating the nodes. So, for example, if I had, oh, this is the bad chalk. No! Why? Oh, it's like sandpaper on my soul. There. So, if you want a cut of this graph, that's a cut. That would also be a cut, right? that would also be a cut. So a cut is not a straight line. I know that, for those of you who are more used to like the crafting metaphors, when you cut with scissors, typically you're trying to cut in a straight line. But in this case, the cut does not have to be a straight line, okay? In fact, the concept of straightness doesn't really mean anything because there's no particular geometric relationship going on here. It's just a graph. Yes?
If we go back to that graph, what would be an example of a line that is not a cut?
A line that is not a cut. That is not a cut because there's nothing on the other side of it.
So every line that crosses into the graph, you can assume it's a proper cut.
Yes, as long as you have a non-empty set of nodes in both camps. Make sense? All right, thank you, folks. See you on Wednesday.